Good day, everybody. Today we are going to talk about material on week 6. So without further ado, I'll share my screen with you. So this is confidence intervals for population mean, population standard deviation unknown. Describe the properties of students' t distribution, construct confidence interval for a population mean, uh, describe the relationship between confidence level and margin of error, find the sample size necessary to obtain a confidence interval of a given width, distinguish between confidence and probability. So describe the properties of students' t distribution. Uh, okay. When constructing a confidence interval where the population standard deviation sigma is known, we use the critical value is z alpha by 2 because the quantity x bar minus mu divided by sigma divided by square root of n as a normal distribution. So basically on the numerator, we have how far the sample mean is located from the population mean. The difference is divided by the standard deviation of the sampling distribution of x bar. And that is sigma, which is population standard deviation divided by square root of n. Here it is assumed that sigma is known. It is rare that we would have know the value of sigma while needing to estimate mu. In fact, it is more common that sigma is unknown. When we don't know the value of sigma, we replace it with the standard deviation S. However, we cannot use Z alpha by 2 because the quantity X bar minus mu, again, the difference of the sample mean from the hypothesized population mean divided by now the standard deviation of the sampling distribution of X bar is written as S over square root of N. And S is the sample standard deviation. And this quantity does not have a normal distribution. The distribution of this quantity is called the student's t distribution. There are actually many different students' t distribution, and they're distinguished by a quantity related to the sample size called the degrees of freedom. When using the student's t distribution to construct a confidence interval for the population mean, the number of degrees of freedom is one less than the sample size. This you have to remember. Degrees of freedom for a t distribution is 1 minus or sample size minus 1. Okay. Student distribution t distributions are symmetric. It is called students t distribution symmetric, just like the normal distribution. That means it's a bell-shaped curve. Okay. However, they are more spread out. So in the top diagram with 1 degree of freedom, that means sample size of 2, the lower curve is the t distribution and the upper curve, solid curve, is the z distribution. As you can see, the lower curve, which is the dashed curve, has wider tails at the left end and at the right end. Further, its peak, where the relative frequency is highest, the relative frequency is less than the relative frequency of the normal distribution of the solid curve on the top. They're more spread out because S is on the average a bit smaller than sigma. Also, since S is random, replacing sigma with S increases the spread. The difference between the t distribution and the normal distribution is greater when the number of degrees of freedom is small. So, like in the case of 1 degree of freedom, and look at the 4 degree of freedom, the dash curve is approaching the solid bell-shaped curve, which is the z distribution. And look at then the 10 degrees of freedom, that means 11 sample size. Here the dash curve, which is the t distribution, almost overlaps the z distribution of the solid curve. So the difference between the t distribution and the normal distribution is greater when the number of degrees of freedom is small. When the number of degrees of freedom is large, S tends to be close to sigma, so that t distribution is very close to the normal distribution. To find a critical value for a confidence interval, let 1 minus alpha be the confidence interval. The critical value is then T alpha by 2 because the area under the student's T distribution between minus T alpha by 2 and T alpha by 2, that is the solid area, is 1 minus alpha, or is it equal to the confidence level. The critical values of T we do not use at table, I will suggest to use the calculator. So let's do, say, for sample size for degrees of freedom 3. That means sample size of 4. And let's assume the area in the right tail is 0.025. So if our confidence level 1 minus alpha is 0.95, the solid area in the center, the area in the two tails is 1 minus 0.95, which is 0.05. So y1, 1 is the total area under the curve, from which we subtract the central area, which is 0.95, to get 0.05 area in two tails. But the T curve is symmetric, just like the Z curve, that is the left half is equal to the right half. So that area in two tails, which is 0.05, area in each tail will be half of the total area in two tails, which is 0.05, divided by 2 is 0.025. So we'll assume the area in the right tail, the white area, is 0.025, and let's assume degrees of freedom is n. N minus 1 is 3. So we go second, then verse in the third line, then scroll down to TCDF. No, sorry, in T. Scroll down to in T, which is number 4. Okay, degrees of freedom area is 0.025, degrees of freedom is 3, and paste. So second verse 4, empty area is 0.025 in the right tail, degrees of freedom is 3, and then go down to paste and hit enter twice. Enter and enter. And the answer is minus 3.182 on the left tail. On the right tail, it is 3.182. So if you go in the table over here, go to the third row, which is degrees of freedom 3. And on the top blue row, draw a vertical line through area in the right tail 0.025 and a horizontal line through degrees of freedom 3. It intersects at 3.182, same as what we obtained with our calculator. So we will be using the calculator instead of the table. So here they have 10 degrees sample, random sample of size 10 is drawn from a population. Find the critical value of T alpha by 2 for a 95% confidence interval. Again, second verse 4. So second verse 4. Area is 0.025 because confidence level is, the area in the center is 0.95. 1 minus 0.95 is 0.05. Divide that by 2. Area in each tail is 0.025. Degrees of freedom is sample size minus 1. 10 minus 1 is 9. We go down to paste, hit enter, and enter. And the answer is 2.262. Why do we get the negative? Because we are doing the calculation for the left tail. On the right tail, the same critical value of T with a positive sign. So it's 2.262. If the desired number of degrees of freedom is listed in the table A3, then if the desired number is less than 200, use the next smaller number than it is in the table. If the desired number is greater than 200, use the Z value in the last row of table A3 or use table A2. We will use the calculator. Okay. Find T alpha by 2 for a 90% confidence interval, sample size 63. So second verse 4, area. Now 1 minus 0.9 is 0.1, divide that by 2.05. So 0.05 is area in each tail. Degrees of freedom is 62. Paste, enter, and enter. And the answer is 1.6698. or 1.67, same as what they got. So that is the way we do it. Assumptions, the assumptions for constructing a confidence interval for a population mean are, we have a simple random sample. The sample size is large, n greater than 30, or the population is approximately normal. When the sample size is small and less equal to 30, we must check to determine whether the sample comes from a population that is approximately normal. So if you have a sample size less than 30, we have to check whether the sample came from a normal population. A simple method is to draw a dot plot or box plot of the sample to look for skewness or outliers. Okay. Decide in each case whether the methods of this section would be used to construct a confidence interval for the population mean. Assume that population standard deviation sigma is unknown. Simple random sample of size 8, sample size less than 30, is drawn from a distribution that is approximately normal. Yes, in that case, we can use the methods of this chapter. Simple random sample of size 15 is drawn from a distribution not known to be normal. We cannot use the methods of this section because the population distribution is not known to be normal. A simple random sample of size 150 is drawn from a distribution not known to be normal, but the sample size n is 150 is greater than 30, so can use the methods of this this chapter. Non-random sample is drawn from a size 212. We cannot use because we always have to depend on simple random sample. And a simple random sample with the following dot plot. Here, the distribution is skewed to the right. It's positively skewed because there is one very large number. Rest of the numbers are between, say, 2 and 7. Therefore, since we have a large outlier or a number which is very large than the rest, we cannot use the methods of this section. The reason is most probably the sample came from a distribution which is population distribution, which is not normal. The tables we are not going to use, so I'll skip over this. Construct confidence interval for a population mean when the population standard deviation is unknown, TI-84 plus. The T interval command constructs a confidence interval when the population standard deviation sigma is not known. This command is accessed by pressing stat and then highlighting the test menu. If the summary stats are given, the stats option should be used for the input option. If raw sample data are given, the data option should be selected. So here are these. A food chemist analyzed the calorie content for a popular type of chocolate cookie. Following are the number of calories in a sample of 8 cookies. Notice the sample size is 8, is much less than 30. So first we have to check whether these numbers came from a population which is well-shaped in distribution. So how will we do that? So press the second button on the top left corner, then plus on top of enter, then number 4. Clear all list on the calculator screen, then hit enter. Done. That means memories have been cleared. Stat 1. Enter the data points in L1. 113, 114, 111, 116, then 115, then 120, then 118, then 116. So these are the points which we have entered in the L1. Now we need to figure out whether this sample came from a population which is approximately bell-shaped. So how will we do that? Well, press the second second button on the top left, then Y equal to on top of it. Then number 1, okay. First line should be flashing on. Second line type, go to the fourth type of chart, which is a modified box plot, which will show us outliers. Fourth type of chart, okay, and hit enter so that it's flashing on the fourth type of chart in type. Then you do zoom, press the zoom button, which is the third key in the top row, zoom and 9. And you will see a nice box plot without any outlier. If there is any outlier, either on the right or on the left, it would have been shown with a separate square box, but there is nothing. So there is no outlier. So that means the sample came from the population, which is approximately normal. Hence, we can use the methods of this chapter. So we have to calculate a 98% confidence interval. So stat, test, scroll down to T interval, which is number 8. Scroll down means with the down arrow key, we go to number 8 and hit enter. Now the input in the first line should be flashing on data. So bring it on data by the left cursor key and hit enter. Okay. The list is L1. So second and 1, L1. C frequency is 1, do not change it. C level is 0.98. Okay. And then you calculate. So with 98% confidence, we can state that the actual population mean is between 112.38 and 118.87. Okay. This is another problem. Sample of 123 people aged 18 to 22 reported that the number of hours they spent on internet in average week. The sample mean was 8.20 with a sample standard deviation 9.84. Assume this is a simple random sample from the population. Construct a 95% confidence interval for mu, the population mean number of hours per week on the internet in that age group. So stat, test, since we do not know the population standard deviation, we have to use the t interval. Scroll down to number 8, t interval, and hit enter. Now the input should be on stats, put it on stats and hit enter. Then it asks for the sample mean was 8.2 and sample standard deviation is 9.84. Sample size n is 123 and sea level is 0.95. And we calculate. So it's between 6.44. So with 95% confidence, we can state that the actual population mean is between 6.44 and 9.56. Okay. 9.956. Okay. And then Excel is not of interest to. Let's do this problem. A potato chip company wants to evaluate the accuracy of potato chip bag filling machine. Bags are labeled as containing 8 ounces of potato chips. Simple random sample of 12. 12 is less than 30. Had mean weight of 8.12 ounce with a sample standard deviation 0.1 ounce. Assume that weights are approximately normally distributed. Since we have a sample size less than 30, but the sample came from a population which is approximately normally distributed, then we can use the methods of this chapter. And this is also a simple random sample. So then this says construct a 99% confidence interval for the population mean weight of bags of potato chips. So stat, test, and we want to go to t interval since we do not know the population standard deviation. Input should be on stats, x bar, sample mean, mean weight is 8.12 and sample standard deviation of 0.1. Sample size is 12 and sea level is 0.99 and calculate. So with 99% confidence, we can state that the actual population mean is between 8.03 and 8.21. Okay. I will not do the same thing again. Relationship between confidence level and margin of error. If we want to be more confident than our interval containing the true value, we must increase the critical value, which increases the margin of error. There is a trade-off. We would rather have a higher level of confidence than a lower level, but we would also have rather have a smaller margin of error than a larger one. So this is a comparison with different levels of confidence. In the left, you have 70% confidence level. That means if you have 100 intervals here, only 77 intervals out of 100 will contain the actual population mean. So this vertical line indicates the actual position of the population mean. And you want a vertical line to intersect these horizontal lines. The horizontal lines are actual confidence intervals. However, you have only 77 out of 70 out of the 100 where the horizontal line cuts the vertical line. That is 30 intervals do not cut the black line, which is the population mean, or the 30 intervals do not contain the population mean. This is now good. Now look at the extreme end, 99.7% confidence level. So if you have 100 intervals or 1000 intervals, 997 intervals will intersect. The intervals of the blue horizontal lines will intersect the black vertical line, which is the population mean. But at the same time, notice the width of the interval is much wider. The width is in wider, so we are losing the accuracy because the width is so large. Hence, The best is the option is the 95% confidence level, where 95 out of the 100 horizontal lines, which are the confidence intervals, intersect the black line, which is the uh, vertical line, which is the line for population mean. Measuring the success rate of the method, the diagram presents 100 different 95% confidence interval. When we construct a confidence interval with level 95%, we are getting a look at one of these confidence intervals. We don't know get to see any of the other confidence interval, nor do we get to see the vertical line that indicates where the true value of mu is. We cannot be sure whether we got one of the confidence intervals that cover mu, or whether we were unlucky enough to get one of the unsuccessful ones. What we do know that is that our confidence interval was constructed by a method that succeeds 95% of the time. The confidence level describes the success rate of the method that used to construct a confidence interval, not the success of any particular interval. Okay. Find the sample size, confidence interval of given width. The formula is given at the bottom is n equal to left parenthesis, inside the parenthesis, z alpha by 2 is the critical value of z multiplied by population standard deviation sigma divided by margin of error, right parenthesis, the whole thing is squared. Okay, let m be the margin of error, population standard deviation is known, the necessary sample size is n equal to this formula. In cases where the population standard deviation is not known, S is reasonably close to sigma for large samples. Given a large sample, n greater than 30, the necessary sample size. What is the difference between the first and the second formula? In the second formula, sigma has been replaced by S because n is greater than 30, and we can use the sample standard deviation. If the value of n is not a whole number, round it up to the nearest whole number. So scientists want to estimate the mean weight of mice that they have been fed with a special diet. A sample of 60 mice have been weighed and the standard deviation S is 3 grams. Estimate the number of mice that must be weighed for a 95% confidence level to have a margin of error of 0.5 grams. So 95% confidence level means Z alpha by 2 is 1.96. So we do a left parenthesis. Inside the parenthesis, we type 1.96 multiplied by the standard deviation, which is 3, divided by margin of error, 0.5, close the parenthesis, and then press the X square button, which is in the first column halfway down, and hit enter. The answer is not 138.29, it's 139. Okay. Machine used to fill beverage cans is supposed to put exactly 12 ounces of beverage in each can, but the actual amount varies randomly from can to can. In a sample of 50 cans, standard deviation of the amount was S equal to 0.05 ounces. A simple random sample of filled cans will have their volumes measured and a 95% confidence interval for the mean volume will be constructed. Estimate the number of cans must be sampled for the margin of error point to be equal to 0.01 ounce. So left parenthesis, critical value of Z is 1.96 for confidence level 95%, multiplied by standard deviation, which is 0.05, divided by margin of error, which is 0.01, close the right parenthesis, x square, and hit enter. And the answer is 97. And I'll do this again. Distinguish between confidence and probability. Uh, So what this is basically saying that with 90% confidence, we can state that the actual population mean is between 19.92 and 20.58 because confidence level is the measures the success rate of the method that we have used to measure the interval. It is not that there is a 90% probability that the population mean will fall between 19.92 and 20.58. Okay. Okay, this is done. Let's move to the other section that we have to cover. So slideshow. Describing which method to use, confidence interval. which method to use, constructing determine which method to use. So one of the challenges in constructing a confidence interval is to determine which method to use. The first step is to determine which type of parameter we are estimating. There are two types of parameters for which we have learned to construct confidence interval: population mean and population proportion P. So is a flow chart. So is sigma known? If sigma, population standard deviation, is known, let's go on the upper branch, which is yes. N greater than 30, yes, then use Z method. If N is less than 30, is the population approximately normal? If his answer is yes, the top branch is use T method. Is the population approximately normal? If the answer is no, then consult a statistician. Then we go on the lower branch from is sigma known? No is the answer for the lower branch. And is n greater than 30? If the answer is yes, use T method. If the no is the answer, is the population approximately normal? Yes, then use T method. If it answer is no, consult a statistician. Okay, let's pick one problem from this. Uh, Let's pick last problem. Simple random sample of size 25 has a mean of x bar equal to 17.4 and standard deviation 5.3. The population is approximately normally distributed. We used to construct a 95% confidence interval for the population mean. So the sample size is 25, which is less than 30. Population standard deviation is not known, but the sample came from a population which is approximately normal. We know the sample standard deviation. So we press the stat, highlight test, and because n is less than 30 and we do not know population standard deviation, we will use the t interval. Number 8, scroll and hit enter. Input is on stats, sample mean is 17.4 and sample standard deviation is 5.3. Sample size n is 25 and confidence level is 0.95 and we calculate. And with 95% confidence, we can state that the actual population mean will fall between 15.212 and 19.588. Okay, so I will stop here today. If you have any question, you can always shoot me an email and I'll respond to you as soon as I can. Take care. Have a nice day. I'll see you next time.